1.6, subatomic particles. So we talked about the discovery of the electron and how they figured out there's got to be protons and neutrons in there. So what do you need to know about subatomic particles? Well, I want you to know that protons and neutrons have nearly identical masses. And if we look at their actual masses in kilograms, you see they're really small, 10 to the minus 27 kilograms. But their actual masses are really, really close. They are not exactly the same, but for our purposes, we can consider them to be the same. The difference isn't worth talking about. The mass of the electron is significantly lower, about 1,800 times smaller. So if the proton had the mass of a baseball, a neutron would also be a baseball, and the electron would be a grain of rice. So that gives you kind of an idea of the scale. Electrons are so much smaller that you really kind of don't even have to consider their mass at all. So kilogram obviously is not a great unit for expressing masses of this incredibly small size, so we use a different unit. It's called the atomic mass unit. The abbreviation is AMU, and it's pronounced AMU. It's not AMU, which might be, some interesting relative of an emu. I actually had a student. No, there's a doctor in Reedley. He's building a new clinic. It's Dr. AMU. I'm like, Dr. Atomic Mass Unit. Awesome. Anyway, 1 AMU is 1/12 the mass of a carbon atom containing 6 protons and 6 neutrons. So the mass of a proton or a neutron is approximately 1 AMU. So that may seem like an odd definition, right? 1/12 of something. Why? Why not just say it's this? Basically what they said is, let's take this mass of carbon-12, a carbon atom that has 6 protons, 6 neutrons. If each proton and each neutron weighs 1 atomic mass unit, then that atom should weigh 12 atomic mass units, right? So they're saying we'll take this atom of carbon and we're going to say this is our standard. That's 12 atomic mass units. And so then 1 atomic mass unit is 1/12 of that. And they did that because you have to have some point of reference, and they like to choose things that are reproducible and easy to do that everyone could do. We don't want to have it be 1/12 the mass of my cup filled with water that's going to evaporate or get drunk, right? It's going to change, and nobody else has access to this. Everybody in the world can get some carbon-12 because it's all over the place. So that's the definition. This is a table listing some properties of the subatomic particles. We've got protons, we've got neutrons, we've got electrons. So in terms of atomic mass units, the masses are 1, 1, and almost 0. So you don't need to know these exact numbers, but what I would like you to know is that this is essentially, come on, great. I seriously do think the universe is out to get me sometimes. Approximately 1, and approximately 0. You should know that. The charges, okay, so we saw how they determined the charge on an electron. The charge on a proton is the same value, just opposite in sign. So the actual charge is 1.60218 times 10 to the minus 19th coulombs. Okay, that's really nice and everything. You might possibly need that in a homework problem, but you don't need to memorize that. The charge on the electron is the same number, just opposite in sign. The neutron is neutral and has a charge of 0. What we're interested in are the relative charges. A proton is +1, an electron is -1, and the neutron is 0. So these charges are something that you should also know. Okay? Any questions? When we talk about charges in general chemistry, we're dealing with relative charges. Matter is usually charge neutral. Most objects do not have an electrical charge on them. And that's because in most matter, there's an equal number of protons and electrons, and so there's no charge. But you can get a charge imbalance that develops. One way to do this is take a balloon and rub it in your hair. And then if you pull it away from your hair, depending on how long your hair is and the texture of your hair, you can get your hair to stand up. Why does it do that? Because you've disrupted the electrical balance. You've got more electrons. I don't remember which is negative and which is positive, but let's say the balloon's negative. The balloon is going to have more electrons and your hair is going to have fewer electrons, and then they're going to be attracted to each other, and we call that static electricity. It's static because it's not moving, but it's an imbalance in electrical charge. The way static electricity gets discharged is through a small shock. So, when the air is very dry, if you shuffle your feet on the carpet with your socks on and then you go touch a metal door jamb, you may get a shock. Have you had that happen to you? It doesn't happen nearly as much here. My parents live in Minnesota, and it's like crazy dry in the winter there because it's so cold outside, and then you run the heater inside and it dries everything out. And I remember the last time I visited them in the winter, I was trying to sleep, and the room was completely dark, and every time I turned over, I saw these little flashes of light, and I'm like, what the heck? Am I hallucinating, or what is going on here? And I thought about it for a while, and I realized that it was static electricity between my body and the sheets when I was rolling over, and in the pitch black, you could actually see them. Very strange, very strange. There's weird science everywhere. Another place we see this is in lightning. Okay, so lightning is a result of a charge imbalance. Negative charge building up in the clouds, positive charge building up on the ground, and when it re-equalizes, we get this flash of lightning. And that is so dramatic and explosive almost, so much energy that then there is a sound associated with that, and we hear the thunder. Any questions? Nature does not like positive and negative charges to be separated. So you can separate them, but they will get back together as soon as they can. The number of protons in the nucleus of an atom defines the element. I sometimes think of atoms as being like people. It's hard to visualize atoms because we don't have pictures, right? We can't see them, they're too small. And so they're kind of abstract, and it's hard to remember stuff that's very abstract. And so I try to relate it to everyday life type things. So in some ways, atoms are like people. The protons are like the personality or the soul of a person. You can't change who you are, but you can change what you look like. And so the electrons, which are on the outside of the nucleus in this electron cloud, electrons can come and go. But the number of protons doesn't change. You can cut your hair or dye it fuchsia or change your clothes or not wear clothes or, do all kinds of things to change your appearance, but you can't change who you are. So the number of protons defines the element. It's called the atomic number. It's given the symbol Z. I don't know why. I really should look that up because it bothers me every time I lecture on this. Why is the atomic number Z? Wouldn't it make more sense for it to be A? Wouldn't that make more sense? No, it's Z. So if we look at a helium nucleus, it has 2 protons. All helium nuclei have 2 protons. Carbon nucleus, 6 protons. Every single carbon nucleus has 6 protons. If it has 7 protons, it's nitrogen. It's not carbon. It defines what element it is. We don't need to memorize these, although sometimes we use them enough that we start to remember them, because we're always going to have access to a periodic table. So on the periodic table, we have the element symbols, and this one has the element names. And then above the element symbol is a whole number. That is the atomic number for that element. So if I asked you, how many protons in the nucleus of a lead atom? Well, you search around and you find lead. Here's lead, its symbol is Pb, 82. 82 protons. So there it is listed, and it's up on the wall, the number of protons in the nucleus of atoms of each element.
Oh, I looked it up.
Mhm.
It's German, or Zoll is German.
Oh,
Number, or,
thank you. Thank you very much. It comes from the German. That's why it's Z. Excellent.
There you go.
Isn't Google wonderful?
Yes.
Yeah. So on the periodic table, we've got a unique atomic number, a name, and a unique chemical symbol for each element. You should be familiar with these from your previous chemistry class and also from that list of element names and symbols that I told you to memorize. If you haven't done that yet, you need to get on it. The chemical symbol for an element is 1 or 2 letters, and the first letter is always capitalized, the second letter is never capitalized if there is one. Oftentimes, the symbol is the first or the first and second letter of the element's name, but that's not always the case. So we see that He is the symbol for helium. That's the first 2 letters. C is the symbol for carbon. For calcium, do you remember what calcium is? Ca. They couldn't use C because C already meant carbon, so Ca is calcium. Carbon also starts with Ca, you just have to remember which one is which. But some of them don't seem to make much sense. Like Na for sodium. There's no N, there's no A in sodium. How did they get that? Well, the original name used for sodium was the Latin name natrium, describing where it came from. It came from the ocean, the sea. So natrium is the first 2 letters of the Latin name. So just like our newly found explanation for why the atomic number is Z, there is a good reason for the symbols that don't seem to make sense. And we just have to memorize them. And it's a little bit like memorizing the odd verb conjugations in English. You practice and you get corrected and you use them and then you remember them. And someone coming in and trying to learn English, heaven help them. Our language is very irrational in many ways. So all atoms of a given element have the same number of protons. The number of neutrons can vary. And this is where they had to adjust, make a modification to one of Dalton's ideas in his atomic theory that all atoms of a given element are identical and have the same mass. Well, they all have the same number of protons, but the number of neutrons can vary. And since the protons and the neutrons are the massive particles, the mass also varies a little bit. So when you have atoms of the same element, same number of protons, but the numbers of neutrons are different, those are called isotopes. So isotopes are atoms of the same element, but they're a little bit different. For an example, neon. All neon atoms have 10 protons. But then there's 3 variations of neon atoms, 3 isotopes. One has 10 neutrons, one has 11 neutrons, one has 12 neutrons. That's not something that you can predict from the periodic table, and it's not something I expect you to remember, that neon is 10, 11, and 12. So each of these exists. They each have a slightly different mass, and they are not necessarily present in equal amounts. Because there's 3 of them, that does not mean that 1/3 of the neon atoms have 10 neutrons. What we call the abundance, or the actual relative amount, is the natural abundance of the isotopes. And that's something that just has to be measured experimentally. They used to think that was constant. No matter where you got your neon, the percent of neon with 10 neutrons was exactly the same. Now we know that there are slight variations, and that's due to advances in the ability to measure things like that. So the sum of the neutrons and the protons in an atom is called its mass number. And that is represented by the symbol A. See, that's what I would like to switch those around, but I should petition scientists worldwide. I don't think it's going to do any good, so I won't waste my time. So A equals the number of protons plus the number of neutrons. And then we have to have a way to symbolize which isotope are we talking about. Many times, we don't care, we're just dealing with the average, a big sample, but sometimes we're dealing with one particular isotope. So we need a way to indicate that. This is called a nuclear symbol. So we have the chemical symbol for the element, and then as a superscript on the left side, we have the mass number, that's the protons plus neutrons, and a subscript on the left side is the atomic number. So these are the designations for the 3 isotopes of neon. Notice they all have 10 protons. Their mass numbers are different though, 20, 21, and 22. So how many neutrons in this first one? Well, you take the mass number, which is protons plus neutrons, you subtract the number of protons, and there you have the number of neutrons. So if you have a hard time remembering which goes on top, the big number or the small number, it's the big number because it's stacked up so that you can subtract and find the number of neutrons. I do like that.
Do we ever have a fewer amount of neutrons than
You can have, I think you can have a fewer number of neutrons than protons. The mass number obviously can't be smaller than the number of protons, though. There are isotopes that have no neutrons.
super
Hydrogen.
unstable?
Hydrogen has 1 proton, no neutrons, 1 electron, little guy. Another way to notate different isotopes is using a chemical symbol with a dash and the mass number. Because do we really need the atomic number on there? No, we have periodic tables. We know what the atomic number is. We just look at the periodic table, it's fine. So here, Ne20, or using the full name, neon 20. This is the mass number. If we want to know the number of neutrons, we look on the periodic table and see that, oh, neon has 10 protons, and we subtract that from this mass number, and that gives us the number of neutrons. So just summarizing all of this, here are the 3 different isotopes for neon and the different ways we can represent them. Each of them has 10 protons, but the number of neutrons is different. The mass numbers are different also because the masses are going to be different. And then here's the natural abundance, usually expressed as a percentage. So 90.48% of neon is this neon 20. Less than 1% is neon 21, and less than 10% is neon 22. You don't memorize those either. Okay, any questions? So you should be able to answer questions like this. What are the atomic number, mass number, and symbol for the carbon isotope with 7 neutrons? Well, atomic number, what does that tell us? Number of protons. So we get that from the periodic table. So we look at the periodic table and we find carbon. How many protons does carbon have? 6. So the atomic number, Z, is 6. And then it's asking for the mass number. The mass number is protons plus neutrons. So the mass number A equals the number of protons plus, how many neutrons does this one have? 7. And we know that because they told us. So the mass number is 13. And the symbol. So they're not asking for all 3, but let's just do all 3 to practice. So what's often called the nuclear symbol, we'll put the element symbol C in the number of protons, bottom left, and the mass number, 13, on the top. So that would be an acceptable answer, or we can call this C-13, or we can call this carbon 13. Any questions? Here we're given a symbol for an isotope and asked how many protons and neutrons are present in this atom. Well, how many protons? 19. It's just given to us right there. This 19, this is the number of protons. We could also look on the periodic table and find potassium. and see that its element number 19, it has 19 protons. How many neutrons? 20. So we got 39 minus 19 is 20. That's the number of neutrons. 20 neutrons. Any questions? What about the electrons? Well, atoms are charge neutral. So the number of protons and the number of electrons has to be equal. So that number on the periodic table that gives us the number of protons also gives us the number of electrons in a neutral atom. But like I said when I was talking about atoms as people, the electrons are kind of like the clothing that the atom is wearing, and you can change your clothing, you can make your outside look different. And so atoms can gain or lose electrons, and when they do, they become charged. And then they are called ions. So if it's got a positive charge, like Na+, that's a cation. Cations are positive charges. That's not a cation, like maybe a short for vacation. It's a cation. Negatively charged ions, like F-, are called anions, and that's not a relative of an onion, an anion. It's an anion. I would probably have a hard time not remembering this at this point in my career, but I remember as a student struggling with which of these was the positive and which was the negative. So I like cats. I have positive feelings for cats. Cations have positive charges. If you don't like cats, you'll have to come up with something else.
Well, I went with the cation has a T that looks like a positive symbol.
I like that. So cation has a T in it. Let's actually write with a pen. Cation. That's good. I like that. So here we have this positive in the middle of it. Cation. Cations are positive, anions are negative. Any questions?